In this video, I'd like to talk about this paper called a ConvNet for 2020s. It imitates some design principles from Swin Transformer and makes a new CNN architecture that achieves even a better result than Swin Transformer and all Vision Transformer counterparts. So yeah, let's talk about that. This figure at right compares ResNeXt-ify shown in blue with Swin Tiny shown in orange. And the reason why these two variants are compared is because of having the similar gigaflops. And also ResNet 200 and Swin base are shown in a gray color, and we are having only estimate value just to see the performance gap. And the whole purpose of this paper is to improve the ResNeXt-ify architecture and make it as good as Swin Tiny or even better than that. But as you see, the accuracy of ResNeXt-ify is reported as 78.8% on ImageNet dataset. But actually, when you look at the original paper, you wouldn't see that. And that's because here they're having a different training techniques. So originally, the performance of ResNeXt-ify is 76.1% on ImageNet. But using the following techniques, which is close to DEIT, a variant of Vision Transformers, we can improve it and make it as good as 78.8%. But what are these techniques? The first thing is using AtomW optimizer instead of SGD. The second thing is extending the epochs from 9D to 300. And the third thing is adding these type of data augmentations: mix-up, cut mix, randognment, and random raising. And if you don't know what are these data augmentation already, I will show you. They are so easy to understand. Assuming we have an input image from a cat, then mixup says we can create a new type of data that is a combination of this class and another class, let's say the dog class. And we overlay the dog class on the original image and we create a new data. But what happens to the label then? So assuming that the cat has label 0 and dog has label 1, then the label depends on the weight that we add the dog image to the original image. So as you can see, for example, in this scenario, since half of the pixels are coming from the cat image and half of the rest are coming from the dog image, then the label, instead of being 0 or 1, it would be something such as 0.5. The other thing is cut mix, that we kinda replace a portion of the image with another class, which is in this case the dog image. And what happens to the labels in this scenario? We just say what are the number of pixels that are for the cat image and what are the number of pixels that are for the dog image, and what are the total pixels. Having these three values, we can kind of compute a proportion of the image that belongs to the cat image and the proportion of the image that belongs to the dog class. And then by having these two proportions, we can consider them as weights. And then the new label would be a weighted sum of the original labels. And the other thing is rand augment, which we do simply just some random augmentations such as shearing and color jittering and that type of things. And the final thing is random raising. So for random raising, we just pick an area of an image randomly and we fill that with a noise data. In this case, you can see it as a gray value, but it could be something such as a random Gaussian distribution. So yeah, these are the data augmentations that we can add. And the other thing is regularization schemes such as stochastic depth or label smoothing. For stochastic depth, it is something similar to dropout, and we just randomly select one residual block and we remove it during training, but during inference we have all of them. And label smoothing is another technique which is so useful. To know what that means, let's just assume that this is our one hot encoded label, that the class 0 is having 1 and the other classes are having the value of 0. Then let's just say our output prediction of our model, the logits, are having these values 10, -10, and -50. After applying the softmax, the first value wouldn't be exactly 1, it would be a value very close to 1. And the other elements in the vector are having a value very, very close to 0. But it isn't still perfect. I mean, it isn't still 1 and 0 and 0. So for our model, it is not enough. So it still tries to make it better and increase the value of 10 and decrease the value of -10 and -50. And the optimal value would be something such as positive infinity for the first element and negative infinity for the other elements. And yeah, that kind of make our model to overfit, and that's not good. So in label smoothing says, assuming that this is our label vector, what we do is that we subtract the element 1 with a value of alpha, which is a hyperparameter, and then we distribute this value over the other elements. So it would be plus alpha over 2 for the other two elements. And then by having this operation, since our vector isn't 1, 0, 0, then it wouldn't force our model to have a positive infinity for the class and negative infinity for the other classes. And that's kind of a regularization that we can add. But anyway, having all these 4 modifications, we can increase the accuracy by 2.7%. And yeah, that's the training techniques. But now let's just talk about the main modifications that they did and then make the ResNet architecture even better than Swin Transformer. The first modification is changing the stage compute ratio. So when we look at the original Swin Transformer architecture, we can see this. We have 4 stages and the compute ratio is 1131 because in first stage we have 2 Swin Transformer blocks, and in the second stage we again have 2 Swin Transformer blocks again, but for the third stage we have 6, and again for fourth stage we have 2. And if we divide these values by 2, we reach this compute ratio, which is 1131. But for the ResNeXt-ify, we do not have this compute ratio. In ResNeXt-ify, we again have 4 stages, and each stage are having a couple residual blocks, and the only difference in the stage is different spatial resolution. But when we look at the number of blocks in each stage, it is this, 3, 4, 6, 3. So they said, let's just change this compute ratio and make it the same as Swin Transformers. So they changed it to 3393, which again, if we divide them by 3, it is still having the same compute ratio, which is 1131. And by applying this simple modification, we increase the accuracy from 78.8 to 79.4. And the gigaflops also increases from 4.1 to 4.5. The other modification is changing a stem to Patchify. So if you look at the ResNeXt-ify architecture, before the stages, we have a block called the input stem, which has a 7x7 convolution destroyed of 2 and a max pooling. And it does nothing but 4 times downsampling, because the original images that we give to the model are having resolutions like 224 by 224, and they have lots of pixels that they are just redundant and they do not give us any information. And by doing this downsampling, we end up having a smaller resolution like 56 by 56, and the pixels are having more semantic. But Swin Transformer uses 4x4 patch size instead. And they said, yeah, we can kind of use a 4x4 convolution with a stride of 4 for this 4 times downsampling. And they did that, and that increased the performance by 0.1% and also decreased the gigaflops by 0.1%. The other modification is ResNeXt-ify. So what was the idea behind ResNeXt? We could say that, yeah, residual blocks are efficient. We can do a group of them at the same time and have a new parameter, which is group size. And here they said we can use depthwise convolution, which is a special case of group convolution. And in depthwise convolution, we have this figure which explains what happens. We apply the convolution for the first channel, which is the red one, with the fourth channel of the kernel, and then the second channel of the input with the second channel of the kernel, and the third channel of the input with the third channel of the kernel. So we end up having the same number of channels for the output as the input. So we can kind of interpret this depthwise convolution as a group convolution where the group size is the number of input channels. And by doing that, the performance becomes much worse. It will become 78.3. So what's the point of that? Well, the point is that the gigaflops decreases from 4.4 to 2.4. And now we can increase the width, which is the number of channels, from 64 to 96. And by doing that, the performance increases to 80.5%. But the gigaflops also increases to 5.3. So you might say, yeah, we could do the same thing without using the stepwise convolution, and you are totally correct. But if you do that, you will end up having much higher gigaflops. And by doing this, we kind of do an engineering technique that we increase the performance while the gigaflops wouldn't be too high. And the other technique is inverted bottleneck, which we can say for every MLP block that we have in every transformer, we have some input with an x dimension, then it goes to a linear layer, and that increases the dimension to 4x, so it makes it 4 times bigger, and then we apply a linear layer again, which decreases the dimension from 4x to x. But as you can see from this figure A, what happens in ResNet is that we apply a 1x1 convolution, and that decreases the channel dimension from 384 to 96, which is 4 times downsampling, and then we apply a 3x3 convolution that doesn't change the number of channel, and the whole point is to capture some local features in the image, and then we again apply a 1x1 convolution that increases the channel dimension from 96 to the original 384. But they said we can apply this inverted block that has the same technique as the inverted bottleneck in transformers. And now originally we say let's just skip the number of channels as 96, and by applying 1x1 convolution we can increase it to 384, which is 4 times upsampling, the same thing that MLP does in transformers. And we apply these 3x3 convolutions in 384 dimensions, and then we apply a 1x1 convolution again to downsample the channel dimensions from 384 to 96, which is 4 times downsampling. And by applying this inverted bottleneck technique, the performance increases by 0.1%, but gigaflops decreases from 5.3 to 4.6. But before understanding what happens next, which is having larger kernel sizes, let's just modify the architecture a little bit. So as we saw from this figure B, we just changed the channel dimension ratios to make it something similar to MLP in transformer, which is 4 times upsampling, doing something with it, and then 4 times downsampling. But in figure C, they decided to swap the position of 3x3 convolution and 1x1 convolution, and do the upsampling and downsampling only on 1x1 convolutions. So the 3x3 convolution happens with 96 dimension, and then there is a 1x1 convolution that increases the channels to 384 and then decreases from 384 to 96 again. And that is more similar to what happens in transformers, because now instead of doing attention at first, we are doing 3x3 convolutions, and then we have a 1x1 convolution which only changes the channel dimension and has the same role as the MLP in the transformers. And now by having this architecture, we can try larger kernel sizes. So instead of 3x3, let's just try 5x5 or 7x7 or something bigger, because they realized that in Swin Transformer they're using window size of 7x7, and so without doing anything, only by swapping the position, the performance drops, and the gigaflops also drops because we are applying the 3x3 convolution on 96 dimension, not 384, which is used to be. But by increasing the kernel size to 5x5 and 7x7, the performance increases. until a level which is 80.6, the same thing that we already had. But now the point is that the gigaflops decreased from 4.6 to 4.2. But as we increase the kernel size to something such as 9 by 9 or 11 by 11, the model actually overfits and the performance becomes worse, the gigaflops increases, so they said, yeah, let's just stick to 7 by 7 kernel size. And yeah, these are the general modifications that they did. And there are some micro design, some small modification that they also did and improved the performance even further. So the first thing is replacing the ReLU activation function with GELU, because in transformers we usually use GELU instead of ReLU, which was originally used in ResNet architecture. And by replacing ReLU with GELU, the performance becomes the same, the gigaflops remains the same, so they realized that changing the activation function is pointless, but they said since transformers are using GELU, let's just stick to GELU again. So since now we're using GELU, and then they realized that when we look at the Swin Transformer block, we only have one GELU, which is here. But for the ResNet block, we have a ReLU here and then a ReLU here. We have more activation functions compared to Swin Transformer. So they said, yeah, let's just use fewer activation functions and only one GELU activation function per each residual block, which is more similar to the Swin Transformer block. We are having a 7 by 7 convolution, which has the same role as the attention in Swin Transformer block, and then we have a 1 by 1 convolution with a GELU activation function between, which has the same role as the MLP in Swin Transformer block. And by removing this activation function between 7 by 7 convolution and 1 by 1 convolution, the performance actually increases from 80.6 to 81.3, which is so strange. By having less nonlinearity, we can have even a better performance. And then they realized we are using too much batch normalization between every convolution blocks. But in the Swin Transformer block, we are only using one layer normalization before the MLP. So they removed the batch normalization after 1 by 1 convolution blocks, and that increased the performance by 0.1%. And then they said they are using layer normalization. We are using batch normalization. Batch normalization has some disadvantages. Let's just replace that with layer normalization. And they did, and the performance increased by 0.1% again. And yeah, this is the new architecture block that has a layer normalization instead of batch normalization, a 7 by 7 at first, which has the same role as attention, and 1 by 1 convolution with the same role as MLP. And the final thing that they did is that they realized that, as you can see on the stage 4, there is a downsampling module at first, that in downsampling, we are using a 1 by 1 convolution with a stride of 2 to do this downsampling. And on the residual path, we also use a 1 by 1 convolution with stride of 2 to do this downsampling. But they realized that in Swin Transformers, we are using 2 by 2 convolution with a stride of 2 for downsampling. So they said, let's just replace that. And by removing those 1 by 1 convolutions and using this 2 by 2 convolution with stride of 2, the training actually diverges. It becomes unstable, and after some point, you cannot really train that. So yeah, there is a new challenge. And they said, what should we do? So they added layer normalization before this downsampling, and surprisingly it fixed. So that gives us a new insight. So whenever we do downsampling, training becomes unstable if we do not normalize the intermediate values that we have in the middle. And by doing that, the performance increases to 82%. So now, by having the same gigaflops as Swin Tiny, this new proposed architecture, which we can call it ConvNeXt Tiny, is 0.5% better on ImageNet, which is awesome, only by using convolution operations. And yeah, then they said, let's just make it scalable and have different architectures like ConvNeXt Tiny, a small, base, large, and X large. the same way that transformers have. And yeah, this is the comparison between Swin Transformer and ConvNeXt. And as you can see, in every scenario, ConvNeXt is better than Vision Transformer counterpart. But what is even more interesting is that people usually think that vision transformers, transformers in general, they require a huge amount of data to learn a good representation and beat the convolution counterparts. But actually, they also pre-trained on ImageNet 22K and fine-tuned on ImageNet 1K, and still ConvNeXt is performing better. So yeah, that's another surprising result. And for other tasks such as object detection and semantic segmentation, they changed the backbone and tried with Swin and ConvNeXt, and in all cases again, ConvNeXt achieves a better result. So yeah, that was very interesting to me. I liked it to share with you. And if you enjoyed it, don't forget to like and subscribe. And until the next video, goodbye.